Okay, folks, welcome back. Hope you had a good lunch. We'll try to keep you awake this afternoon as you digest your food. So we'll try to have a lively example here. And we talked about a lot of theories. Now we're going to talk a lot of examples. And then we'll get back to theory.
All right, so now what we're going to do now is go through one latent class analysis example from beginning to end. All the other examples we've looked at, sort of the results and then the input, and not put it all together. So the example that we're looking at is going to be taking some new data, antisocial behavior data. It's also a large national survey, part of that same NLSY, National Longitudinal Survey of Youth, that we looked at the alcohol items from. Anyway, the data from this that we're going to look at are 17 antisocial behavior items. They were collected in 1980 when the respondents were between 16 and 23. We're going to also look at background variables of age, gender, ethnicity, and these items assess the frequency of behaviors during the past year. And we have over 7,000 respondents that we're looking at. So as an example of the items, we have property offense items in these 17, person offense and drug offense. And for example, property offense would be damaging property, shoplifting. You can see the rest. Person offense, fighting or threatening people, and drug offense, using marijuana or other drugs. And the items are binary. They were dichotomized, 0, 1, with 0 representing never having the behavior in the last year and 1 representing having it in the last year. And the question we're looking at is, are there different groups of people that have different profiles on these antisocial behaviors? And we'll be trying to answer that question using latent class analysis. So, first of all, a summary, and then we'll look at the input and the output in more detail than we have. So this is a table similar to what we've looked at. So when you are set out to do one of these types of analyses, it's a good idea to run the 1 perhaps, but at least the 2, 3, 4, 5, 6, or whatever number of classes you think you're going to be looking at, a few below and a few above, and then creating a summary table like we have here, where we have the various fit statistics that we've been talking about, and where we can assess whether they help us to decide on the number of classes. So here we have our log likelihood, which goes down considerably from 2 to 3, or up rather, considerably from 2 to 3, and from 3 to 4, there's also a fairly substantial increase, and 4 to 5 less, etc. So here you might consider 4 classes looking at that, or 5. And we're going to look at a plot of these also, so you can see better. When you plot them, you can see where things flatten out on the log likelihood. And then we have our BIC where we look for a minimum. So we want it to hit a minimum and then start going back up. But if you look here, it just continues to go down. We never hit a minimum, even with 6 classes. So it seems that BIC is not really helping us in this situation, and that sometimes happens. And then we have these other alternatives that we haven't really talked about. And then we have what Karen Nyland studied, the naive chi-square, and that is the difference between the two, minus 2 times the log likelihood difference, which is not distributed chi-square in this situation. So that's why we refer to it as naive chi-square. And that could perhaps point to 4 classes. And here's a situation where neither Tech 14 or Tech 11 show any increase in the p-values to help us determine the number of classes. So here's a situation where really we haven't gotten much help at all from any of these tests. So we need to consider other information. But like I told you, sometimes plotting the BIC or plotting the log likelihood can be informative. And here we see that it increases and then it starts leveling out at 5 classes. So that could be an indication that around 5 classes might be a good place to look. So previously we've looked at plots, profile plots, to help us when the statistics didn't help us. Here what we're doing is we're going to interpret the classes based on their profiles and see whether that can be helpful. So for example, we have class 1, and when we look at the profile, we see that class 1 seems to be high on all of the antisocial behavior items. So it's not clear that it's one or the other types of items is more prevalent. Whereas class 2 has conditional item probabilities that are highest for the drug items. Class 3 for the person offense items, and class 4 seems to be a more normative class where the only item that has a relatively high conditional item probability is smoking marijuana. So these are our 4 classes. When we go over and try to make the same kind of interpretation for the 5 classes, class 3 is the drug class, then we also have a person offense and a normative class, classes 4 and 5. We still have a high class, but then in addition, we have a property offense class. So we could consider 4 classes or 5 classes. When we looked at the 6 class solution, the only difference was that class 2, the property offense class, seemed to divide up into 2 classes, but that were very similar in latent profiles. So what we decided here was to go with a 4-class solution. And ultimately we're going to see that the reason we did that is the 5-class solution was very, very difficult to replicate. And so we went with the 4-class solution. Okay, so now I want to go over the input that we use to do this. And I think now you're familiar with the classes option, and here we always call the categorical latent variable C, although you don't have to do that, and this is for 4 classes. But as you know, we did it for 1 through 6 classes. And here's an option that you might not have seen. Categorical option in the variable command says that property through gambling, the variables here in the used variable list, are categorical. And the categorical option is used only for dependent variables. The scale of independent variables or covariates does not affect model estimation. As in regular regression, they can be binary or continuous, and they're always treated as continuous. So all of the options like categorical, nominal, count, they're used only for dependent variables in the model. And then we have our analysis command, type equals mixture. And in the model command, as I mentioned, the overall part of the model applies to all classes. In this situation, you'll see that I have commented not needed for everything that I show here in the model command. For latent class analysis, you don't need to specify a model. We have default starting values, and it's unnecessary. If you want to specify the model because, let's say, you want a particular class to be the last class or the first class or whatever, you can do so by, in the class-specific parts of the model command, %C number 1%, for example, %C number 2%, you can specify threshold starting values. Thresholds are specified in brackets. Means, intercepts, and thresholds are all specified using brackets. And here, the name of the variable is property, and $1 means it's the first threshold. So we're having binary items here, but it is possible to have ordered polytomous items, and then you have more than one threshold, and you want to be able to refer to those thresholds. So we use the convention by adding $1 or $2, $3 to the end of the variable name to specify which threshold it is. And binary items have two categories, so they have one threshold. And here, asterisk, that's the first time we've seen that. That represents a starting value, so that says it's free, and the starting value for all those items is 0. And likewise in class 2, we have free with starting values of 1, and then 2 and 3 in classes 3 and 4. So if you want to, you can specify all this and give starting values, but it isn't necessary. We have default starting values. In the output command, you can ask for Tech 8. That's the technical part, and it comes to the screen, and you can see how the analysis is progressing. And Tech 10, which we talked about earlier, and that's the residuals, the univariate, bivariate, and response pattern residuals when you have categorical outcomes. Save data. I give a name where the data will be saved, and then I say save is cprob, which is the posterior probabilities. So you'll save all the analysis variables and also the posterior probabilities and most likely class membership. So this is what you do when you want that most likely class membership variable that we showed you in a couple of tables and plots. Okay, so now we're going to take a look at some of the output. So under tests of model fit, this is where we picked up the log likelihood values that we put in the tables. So you get the log likelihood values, then you get certain information criteria, the number of free parameters, the AIC, BIC, sample size adjusted BIC, and entropy all come at the beginning of the results under tests of model fit. And then here are the two Pearson and likelihood ratio chi-squares. They come next, and once again, when you have more than 8 categorical indicators, it's likely that the table, the multi-way frequency table, will have too many sparse cells to make that test meaningful. So if the values don't agree, which they don't here, then you would really not look at either of them. And you can see down here, we say of the 131,072 cells in the latent class indicator table, 166 were deleted because they had 0 cells. So you can see how large that table is and how unwieldy it would be to work with. Okay, now here's a part of the output that I need to explain, and that's classification information. So we saw entropy. That's a summary of how well the classes classified people. So that means how clean the classes are, whether people are more in one class than any other class. And so here's from the model. And during the model estimation, people are in all classes proportionally. So you can see class 1 has 672.41594 people, or 9%. Class 2 has 1354.73, or 18%. We have 25% in class 3 and 47% in class 4. And this is the normative class. Class 1 is the high on everything, so you would expect that to be a smaller class. Then we have classification of individuals based on their most likely class membership. So people have a probability to be in each class. And what this table does is tell you how many people have their most likely class membership, so their highest probability to be in class 1. So that's 664 versus the 672 up here. and class 2 has 1237, and you can see the percentages here, 9, 17. Class 3 has 1772, and class 4 has 3653. Then we give another table, and this is the average latent class probabilities for most likely latent class membership by latent class. Okay, so what does that mean? We worked really hard on that title, and it's still not particularly clear, but anyway, so what does that mean? What is this first row? This first row is the 664 people who had most likely class membership 1. Of those, 0.896, or the average of their probability of being in class 1 is 0.896, but the average of these 664 people's probabilities of being in class 2 is 0.057, for class 3, 0.046, for class 4, 0. So that's how, and the way you look at this is you look at the diagonals. The diagonals are correct classification, the off diagonals are misclassification. So you want the and it's not symmetric. So the numbers on the upper diagonal and the lower diagonal are different. But you want the upper and lower diagonal numbers to be small and the diagonal to be high, and that will be reflected in your entropy value. The entropy value is a summary of how cleanly classified people are in this table. Okay, so let's see, what's next here? Okay, here's Tech 10. And if you have binary items, then I would say Tech 10 is probably the best assessment of model fit, even though it isn't really a fit statistic, but the best assessment of what's happening as far as the fit of your model to your data that you can use. So first of all, we have the univariate model fit information. So it's for variable property. We have category 1 and category 2. Now, H0 is the model estimated probability. H1 is the information from the data. And the difference, observed minus expected, is the residual. And you can see that the residuals, the univariate residuals, are 0. So there's no problem there. And these residuals are standardized such that they're z-scores, so the value that you want to be looking for is a number greater than 1.96, absolute value greater than 1.96. And then here's bivariate information. So we have the variable property and the variable phi, and so we still have our H1, H0 columns and our standardized residuals, and we can look down and see where we have large values. So these are less than 1.96. So here we have a property, category 1, shoplift, category 2, so that cell of the table. So you have a 2 by 2 table, and you've got 1, 1, 1, 2, 2, 1, and 2, 2. So this tells you which cell of the table may not fit well. So here it's cell property value 1, shoplift value 2. That cell has a residual greater than 1.96. And so do these others. So these are situations where what that would say to you, if you see this, is you might want to add more classes. That might take care of the problem. Or you might, if it's not pervasive, it's just one situation, one pair of variables that has a problem, you might want to add a residual correlation to the model. And this afternoon, Bengt is going to give an example where we add a residual correlation. So the two things that you can do to get around these large residuals is, one, add more classes to take care of these relationships that haven't been totally explained by the number of classes you have, or if it's not a general problem, then add a residual correlation specific to, in this case, the property and shoplift variables. So Tech 10 is very useful. Then what do you get? And we'll go through this fairly quickly. You get a lot of output. So we have, I'm going to take this because I wrote what the classes are on it so I don't forget. So class 1 is the high class. So we have low thresholds, which are equivalent to high probabilities. So we give you the results in two ways. We give you the logits here, or the thresholds, and if they're very low, then you have the high probabilities. We also give it to you in probability. So for class 1, the high class, here are all of the variables, property through gambling, and you can see that we have the low thresholds, the high probabilities, and that's what we said about this class. They had high probabilities on everything. And then we have class 2, which is the drug class, and so we would expect to see pot having a low threshold or a high probability, and drug, I think this might be taking drugs in general, so that's what defines class 2. And then we have class 3, which is the person class, so we would expect the low probabilities to be related to something about threatening here and fighting. So we give you these logits, and then the fourth class is the normative class. So first of all, we give you everything in thresholds, and then we give you information in the probability scale. And this is just a partial output. And this is class 3, which is the person class. So you can see the higher probabilities are related to the lower thresholds that we looked at. Threatening has a probability of 0.68, fighting 0.533. So we give you the logit values and the probabilities, unless you have covariates in the model. And then I want to just show you this plot just as an example of when a plot isn't necessarily helpful. So, here things kind of go through each other and around. It's not like we have the high, the low, the high on some, low on some. This is a situation where it might not be helpful to look at a plot to help you decide, and you would need to determine substantive type things. So as I said before, we looked at what the meaning of the classes was to determine how many classes, not using the plots like we were able to do earlier. So I guess what the bottom line in the message is that there are many, many things to look at when you're doing this type of analysis. Not all of them are always helpful, and so you have to look at a lot of different ways to try to come to a conclusion about the number of classes. And as Bengt was mentioning, in some situations there may not be a strong enough signal in your data to really answer the research question you're trying to answer, and you may not find any meaningful classes, in which case, of course, you should not publish a paper on it. But these are, so I guess what we're trying to say is when you get into this analysis, a lot of times I get questions on support where I feel like people have started at the end and just put it all in the model command and everything and run it, and then it's sort of like, but now what, or what does this mean, or why didn't it work? But you really have to, this is a thoughtful type of a procedure, and the most important thing you bring to it isn't your data and isn't a computer program. It's what you know, what you've studied, the question you're trying to answer, and whether it makes sense, what you're doing. So statistics is only a tool for you to use. What you're doing and your own substantive knowledge is really more important. Statistics just helps you summarize the data, helps you depict the data in a way that can answer your research question. It does not take bad data and turn it into good data or create any kinds of miracles. Banks still thinks it does, but I'm teasing. Okay, so now here's just a summary of this. And so once again, just to remind ourselves, class probabilities, those are our structural parameters. This is our combined class, which we call high, and our drug class, person offense, normative. And, this just shows in summary form what we've seen, that the normative class, they have the highest probability of smoking marijuana, using marijuana, and the person offense class on person offense items like fighting, the drug class on using marijuana and other drugs, and the combined class pretty much on everything, and person offenses. So I think I have one last thing to show you before Bengt takes over. And this is when we said save data and we gave file equals and save equals cprobs, this is what gets saved. So the first line represents the data. So these are the antisocial behavior items. So you can see this person didn't endorse any of them. And the first four values on the second line are their posterior probabilities. So they had 0 for class 1, 0.001 for class 2, 0.013 for class 3, and 0.987 for class 4, resulting in their most likely class membership variable being 4, because 0.987 is the highest. And same thing, so then this is the first record. The second record has the data here, the antisocial behavior items. This person had 1, 2, 3, 4, 5 that they endorsed. Their posterior probability for class 1 is 0.005, for class 2, 0.995, class 3 and class 4, 0, and their most likely class membership, 2. So when you save the data, you get your most likely class membership, then you can use that, for example, in the plot of the two factors against each other, where we showed what a class each person was in, or where we had the sum score of the number of items that each person endorsed by latent class. There we used the most likely class membership. And if you have fairly good entropy, probably 0.8 or above, then most likely class membership is an okay variable to use. If you have very low class very low entropy, below 0.8, let's say, then the most likely class membership variable may not really give you the same results as if you did a simultaneous analysis where the latent classes are estimated along with whatever other part of the model that you have.
All right, folks, time for some more general methods knowledge. And actually, I'm not going to start with this slide. I'm going to start with this. Looks much nicer, figure. So this course goes back and forth between applications and theory and between introductory and advanced things. But note that if you feel that a lot of it is very advanced, you have the possibility of now, after this course, not only watch the video of this course for free, but go back and you can even start at topic 1, which is recorded on the web, which starts with linear regression, how to do that in Mplus, goes through the Mplus language carefully for that, factor analysis, structural equation modeling, that topic 1. And topic 2, dealing with categorical variable analysis, no latent variables necessarily, from a very basic point of view, if you really feel that you want to start from the beginning. So we're trying to entice you to take the whole 8-topic series. But if you get to this stage now of seriously doing mixture modeling, latent class modeling, you have to know the following. And that is that mixture modeling takes care you have to take care to do the analysis well. And to illustrate that, we have 4 different cases here, where case 1 is a very easily dealt with case, and going down to case 4, which is a very difficult case to deal with. So what we have here on the x-axis is a parameter, the value of which we want to estimate. And this is just one parameter. Typically, we're going to work with 10, 20, 30, 50, 100, 200 parameters, in which case we would have to show this in a very complex space. So we stay with one parameter. And we're looking at the likelihood, and we want to find the maximum of the likelihood. You want to find this peak. Where this peaks is where the parameter estimate lies. So this value here on the parameter is the maximum likelihood estimate. And we assume that it has this nice peak, just one peak, and a peak that's very sharp. The sharper the peak, the smaller the standard error around the estimated parameter. Often this is the case. Things look like this for say, structural equation modeling. But with mixture modeling, things are typically not that simple, but you have case 2 much more often. That is, you may have, say, 2 peaks, like is shown here. And if you're not careful, you may end up in the wrong peak. This is a local maximum, whereas the global maximum sits up here. And that makes a difference because the parameter estimate is too high here. In the local peak, it should be down here for the global peak. And when you estimate parameters, it's not like linear regression where the parameter estimate is explicit formula, but you have to find the parameter estimate iteratively. You do so also in structural equation modeling. So you have to start with the so-called starting value. So for instance, if you start with a starting value here, and ask the algorithm to find the best peak, it goes by the derivative. The derivative of this is negative, and it points to lowering the parameter value until you get to this point where the derivative is 0, and you know then that you have an optimum. And since it peaks this way, you know that it's a maximum. So that's saying if you start here, you may end up in the wrong peak. If you start here, you may end up in the right peak, which says that we need to have many different starting values, and that is then simplified in Mplus through a function called starts equals. That generates randomly drawn starting values generated automatically by the program. So we start many different starting points to ensure that we're going to find many solutions at the highest likelihood. And we're going to see examples of that for Linda's antisocial behavior example. Case 3 is a little bit harder. It's harder because not only do we have 2 peaks, but the peaks are very similar in height. Whereas in case 2, the peaks were quite different in height. Here, they're hard to tell apart. And in fact, in many complex models, the difference may be only due to numerical rounding off errors, numerical errors. But the choice of the peaks make a difference because there is a distinct difference in parameter values on the x-axis here. So here, you may want to go in and investigate each of the 2 solutions and see what the parameter values are for the 2 solutions. I'll get back to that in a second. Case 4 is the worst case, and you have then 2 peaks that are quite similar, but the parameter values are very far apart. It makes a huge difference in the choice of peaks. So starting from here, from the case 4, peaks are similar, parameter estimates are far apart, difficult situation. Peaks are similar, but the parameter values are not too far apart, a little easier. Here, the peaks are different, so you know that you should choose this value, and here there's just 1 peak. In these 2 cases, you may want to go in and take a look at the different solutions. Let me tell you what I mean by that, by going forward here. If you take this example of ASB, antisocial behavior, on the left part here, this left part, you have the 4-class solution, and on the right you have the 5-class. And what we're looking at here are the log likelihood values for 10 different starting value sets. So you do 10 analyses here. Actually, you do many more, but in the final step, you do 10 analyses. And here is the best likelihood, log likelihood. You see that's better than the one at the bottom, for instance. Minus 41,023 is down here. Minus 41,007 is up here. So this is better. We see that that best log likelihood value is replicated 1, 2, 3, 4, 5, 6, 7, 8 times. And we want to see the best log likelihood value replicated many times for us to know that we have actually searched through the parameter space properly. In the 5-class solution, however, we have this is the best likelihood value. The next one is lower, not as good. But here the best likelihood is not replicated. We don't have several starting values giving that same starting value, same final log likelihood value, I should say. And that's a problem. If you only have one best value but can't replicate it, it is an unstable solution, and it probably indicates that the model is not very well defined. Not very well defined. The model is not very well defined by the data. And therefore, if you took another random sample from the same general population, you may not find a similar solution. Now, if you want to go in and take a look at this, you can ask yourself for the 5-class solution, well, they're different, but they're not that different. And you might ask yourself, are we in case 4, where the likelihood peaks are not very different, but the estimates are very different? Or are we in case 3, where the likelihood peaks are not very different, and the estimate difference is not very different? You can determine yourself where you are by looking at both of these solutions, and you do that by using the opt-seed option. So you can look at the seeds here that are printed. You can specify opt-seed equal to those seeds, and that's a starting value set that is given. Then just one starting value set, one run for this, which you have in your printout, and then you do this run with opt-seed equals 78, 31, 65 to look at that solution. And then you compare the parameter estimates for the two to see if you're in the difficult, dangerous situation, or if you're in this situation where the estimates are pretty much the same, in which case you really have replicated the best solution. It's just that you don't have enough numerical precision here to get down to 1, 2, 3, 4, 5, 6 decimals. Now, the default number of random starts, as it says here, is 10 initial random starts, and then picking the best 2 for 10 initial random starts that are iterated, optimized to a certain point, not all the way, but to a certain point, and the 2 most promising ones are taken all the way. For these data, that was sufficient. Only that few random starts was sufficient for 1 through 4 classes and for 6 classes, but not for 5 classes. For 5 classes, we needed 300 starting values initially and 10 final values to find this best solution here. And now with fast computers, I recommend almost always to increase the default starting value numbers, this default number of random starts. You can read about random starts on the previous slide 116 here, which is taken out of the user's guide. You can read about it in more detail in the user's guide. So that's a little technical comment. And again, if you want to read about latent class analysis, as we have talked about it here, here are some of our favorite articles. Cliff Clogg's handbook chapter, Leo Goodman's 1974 technical paper, for those who are a little bit more technical, talking about that non-identifiability of three-class model with four indicators. This was the applied edited book. Here are two applications to schizophrenia and to medical diagnosis, heart attacks, and here diagnostic agreements, some articles of interest there. And at that point, we'll get back to the issue of latent class analysis with covariates, which we introduced very briefly in the case complier average causal effect estimation, but didn't really take time to introduce. We mentioned multinomial logistic regression, but we didn't really explain what it was. So we start with this picture here, and you have, again, three dichotomous variables for simplicity and latent class variable C. And now we're going to introduce a covariate X here. This looks very much like the picture I showed for the ADHD situation. Typically, modeling is done with where C is regressed on X, but there's no further regression of the items on X. So typically, this broken arrow is left out here. And that's what I indicate by a broken arrow in this case. It's not that common to include. Now, if you focus on the regression of C on X, you have that on your right screen, slide 121. C is categorical dependent variable, and it's polytomous, but it's not ordered. It is not an ordinal variable. We don't assume that it is, at least. But we take the more neutral stance of saying it is an unordered polytomous categorical variable, so a nominal variable, in other words. And there are really three kinds of logistic regressions, or main types. One is binary dependent variable, second is ordered polytomous, and the third is unordered polytomous. And they differ a little bit, but are related as follows. So we're now interested in describing the probability of C assuming category K. What I'm going to say now is relevant also if C had been an observed nominal variable, like choosing the bus, the train, the car, or the bike. So one special case of Mplus is just multinomial logistic regression for observed nominal dependent variables. So we're interested in the probability of falling into, say, the biking category as a function of your, say, age. And that's described by this expression here, e to the power of alpha sub k plus gamma sub k times x. Alpha obviously being an intercept, and gamma being a slope since it multiplies x. And in the denominator, we have the sum over a lot of such expressions to make this into a probability that varies between 0 and 1. And we have a standardization here. We have the last category, capital K. So K varies from 1 through capital K. The intercept and the slope are standardized at 0, so that then, in that case, the exponentiation becomes e to the power of 0, and e to the power of 0 is equal to 1. In fact, that's the 1 that we see in the binary logistic regression. So the binary logistic regression is a special case of this, where you cannot tell if the categories are ordered or not, really. In any case, this model up here implies that the log odds comparing class K, a certain class, to the last class, is this linear expression down here. So it's a log of the odds, which is the probability of one outcome, namely the outcome that we consider, that category, divided by probability for a reference class, in this case the last class. And it's a linear logit. There is a distinction here, though. In the unordered nominal case, note that we have several intercepts, which is related to thresholds. We'll talk more about that later, because they're indexed by k. But we also have the several slopes. So the slope varies as a function of the categories of the dependent nominal variable. If you had a polytomous dependent variable where you didn't, where you had an ordered categories and ordinal variables, the slopes would be the same. There would be no subscript k here. But the more general unordered nominal case will have intercepts and slopes that vary across the classes. So this is the slide 121 is the machinery that orchestrates X influencing C, or in other words, C regressed on X. An example of that is in this book chapter. Sociological Methodology is a book that comes out once a year. It's a very good methods book. And in 1985, Cliff Clogg and Leo Goodman had a great chapter on simultaneous latent structure analysis in several groups. So it's stimulated by the multiple group analysis and structural equation modeling and factor analysis that Carl Jureskog introduced, and here translated into the latent class setting. And you may want to read that chapter, and it's interesting. All of these analyses can be done in Mplus, and it can actually be done without resorting to multiple group analysis. For those of you who know what a multiple group structural equation model is, you know that one alternative to that, to multiple groups, is to have a dummy variable representing group as a covariate. Turns out that all of these multiple group analysis can be done with a covariate, and you can go through the examples and convince yourself that you could do it by getting the same results. You have the data in that chapter. So that's an advanced exercise. So with categorical variables on the response side and categorical latent variables, there's no difference between multiple group analysis and mimic or covariate approaches. However, in Mplus, you could also do multiple group analysis by using the so-called known class option, where the class membership, we talked about latent classes as corresponding directly to having several subpopulations. But unlike the multiple group analysis, the subpopulations are not known. But here, in multiple group analysis, the subpopulations, the class membership is known, and we handle that through mixture modeling, but where you know which class an individual is in. So the multiple group option is possible for when you prefer to do it that way. And back to Linda.
Okay. Thanks. All right, so now just to take an example of adding covariates to the antisocial behavior latent class analysis that we previously did. So in Mplus, it's pretty easy to do this. The covariates that we're going to add are age, male, and black. So you just add those to the used variables list. And there's nothing else that you have to change in the input except, let me just do this, in the model command. So in the model command, the way that we show the regression of the categorical latent variable on the covariates, the multinomial logistic regression, is in the overall part of the model command. We can say either just C on age 94, male, black, or because we have 4 classes, we know the last class is a reference class, we can say C number 1 dash C number 3, which implies C number 2 is in the middle of the list, on the covariates. So this is all you need to do to specify that the model has covariates and that they're to explain class membership. And then on the left screen, you have the normal log likelihood and test of model fit. But what we're most interested in this example, is the results of the multinomial logistic regression. And so here we have class number 1, the high class, for example. Just to reiterate, the first column here under estimates, the parameter estimate, then the standard error of the parameter estimate, and the ratio, which is a z-score. So we see that 2 of the covariates are significant for class 1. So this is the results for class 1, then class 2, and class 3. So how do we interpret these? So we say as age increases, this is continuous, the log odds of being in class 1 versus class 4 decrease because we have a negative coefficient. So in this situation, we're always comparing to a reference class. So here we would say for males, the log odds of being in class 1 versus class 4 are higher than for females. So that's a binary covariate. So that's how you do that. And then the same thing for class 2. We see that age is also significant but positive, and that black is significant and negative. We see in class 3 that we have all 3 covariates are significant. So this is how you will find the results of the multinomial logistic regression of the categorical latent variable C on a set of covariates. Now, we can take the information from here and we can turn the logits or the log odds, which are our parameter estimates, into probabilities. And this is taken from the user's guide. So you know it's important that we have our logit. And in this example, we're making all the covariates be 0 for simplicity. Age 94 is 0, which really is age 16. Male is 0, and black is 0. So that means the logit is equal to the intercept. So here for each class, we have the logit, which is equal to the intercept, which you find right here in your output. You exponentiate those values. And in the last class, the logit is 0. It's the reference class. Then you compute the probability, which is the exponentiated value divided by the sum. And you get the probabilities of being in the latent classes. And then on this next slide, I show you an example where instead of having all the covariates equal 0, we have male equal to 1, black equal to 1, and age equal to 1. So then the logit just becomes a little bit more complicated. It's the intercept plus the regression coefficient times 1 for each of the 3 covariates. And we get these values that we see here, and we just go through the same procedure to get the probabilities. And this is in Chapter 13, taken from Chapter 13 of the User's Guide. And then we can take these probabilities and we can make them into some type of picture that maybe helps us understand better what's going on. So I always have to have this because I can never remember what the classes are. So anyway, here we had 3 covariates. 2 were binary and 1 was continuous. So the 4 boxes represent 2 times 2, the 4 combinations of the binary covariates. So we have white males, white females, black males, and black females. And on the x-axis is the covariate age. And then on the y-axis in all of them are probabilities. So for white males, you can see that when they were 16, they were most likely to be in class 3, which is the person offensive class. And by the time they reach age 23, they're most likely to be in the normative class. For white females, they're most likely to be in the normative class throughout, and etc. So you can take a look at the others and interpret them yourselves. But basically, this is how you might use the information in an article or something to understand what is happening. You can see where, sort of in the white males, where the crossover occurs. Around in between 19 and 20. The probability of being in class 3 goes down more, and the probability of being in class 4 goes up. In black males, you can see the same thing happening, but at a slightly later age. So, these can be informative, these types of plots. And then, finally, some references, which I'll let you talk about, Bengt.
Well, all of these are statistically oriented. None of them, all of them are applied as well, but they're really written on a statistical level. So this is from JASA again. Very good article. Here's an early article that I refer to. And here's an educationally oriented article. These are education researchers, but it's still in JASA, it's fairly advanced. This topic of covariates in latent class analysis has reappeared many times. You see this is from 1988, and then the topic comes back in 1997. So it's been there latent for many years. But I recommend those articles. Applications with covariates are usually embedded in various kinds of application articles in substantive journals. And we'll try to point to those applications as we go further. But I don't have them explicitly here. So now let's, without spending a lot of time on it, I want to give you some variations on this theme. So far we talked about exploratory latent class analysis. But if you remember, the first topic we started with was regression analysis. And when we did the regression analysis, we did it both in an exploratory and in a confirmatory sense, although mostly in a confirmatory way, by which I mean that there were two regression mixture examples which relied on a specific design. One was the design of the throwing these dice, and the other was a randomized design, totally randomly putting people in treatment control groups. And both of those design studies gave rise to confirmatory regression mixture analysis, where certain coefficients were fixed, which they are not in the exploratory analysis. So now we're going to switch to the counterpart to that confirmatory regression analysis in the latent class setting. And we are going to not only move from exploratory to confirmatory analysis, but also move from working with one latent class variable to working with several. One good example of that is twin analysis. And you have this situation of, usually there are two twins, twin A and twin B. Twin A could be the firstborn, twin B the nextborn. And say that you have a measurement instrument. We're starting to draw these in more and more general fashion. This means that you have a set of variables, say a set of binary indicators, and there are apparently 11 of them for twin A, and the same 11 items are given to twin B. You could write out 11 boxes there. So you have a latent class variable CA and a latent class variable CB. And clearly, each twin has its own latent class variable, but they are correlated. Twins tend to act alike. Not only do we have two latent class variables, but we also have certain restrictions. For instance, we may say that we have measurement invariance between the two twins. So we have an equality sitting here. And that is the measurement parameters were the conditional item probabilities, which we represent by the loaded threshold values. They are equal across the twins. So we're assuming that we have measurement invariance. It would seem like that would be a good case for measurement invariance, the twin setting. That would be a likely place to have measurement invariance. And we may even think that you have certain relationships between the parameters of the latent class variables. So we'll take a look at that. Now, the confirmatory aspect of this is not only that we have equality of these measurement parameters specified, but we also say that twin B responses are not influenced by twin A latent class membership, but only by twin B's latent class membership. And vice versa, CB does not influence that box, but only that box. So we don't have these cross arrows going like that. If we allowed that, then we would be no longer in the confirmatory setting. So the question is, how do you impose that here in these ideas in a Mplus setting? We have, first of all, then, two latent class variables, CA with, in this case, 5 categories, and CB in this case with 5 categories as well, 5 classes. So that's the only thing you have to do to work with two latent class variables. Now, if you ignore these, here's the starts command, by the way, asking for 50 initial and 5 final random start values. Parameterization equals log linear. When you have several latent class variables, you have two choices for how to relate the variables. You can either have an association model. This is the log linear alternative, or you can have a regression, as we will see later on. You can say that twin B is influenced by twin A by being the younger twin. Then you would regress CB on CA. Then parameterization would be logistic, which is default. Now, these equalities, measurement parameter equalities on the left screen, are handled by the seemingly complex statements here on the right screen. And actually what we're talking about here is that the 5 by 5 table here, if you look at we're looking at the structural part of the model first, we're imposing a certain restriction on the structural part of the model here. And it is done by these with statements. We are saying that we have a relationship, association between the latent class variable A with latent class variable B. So we're using with here, with being a covariate with. I don't think we used that keyword before. And in fact, we're going to let category 1 for class variable A, covariate with category 2 for class variable B. We're going to give it a parameter label. Wherever we put in parentheses here is a label. And we're going to say that 1, 2 is the same as 2, 1. We're going to have a symmetry assumption here in this twin modeling. And so the association table is symmetric. And same thing, 1, 3, and 3, 1, etc. down. We're also going to say that the marginal parts of the latent class variable A, the marginal logits, which lead to marginal probabilities for CA and CB, are going to be the same. So CA number 1 gets the same number as CB number 1. And same for CB number 2, etc. So together this says that you had the 5 by 5 table. You have 5 classes for A, 5 classes for B. Is symmetric. The upper triangle is the same as the lower triangle. And the marginal probabilities are the same. So that might be a reasonable hypothesis for twins. Then, slide 135, we go to the measurement part. So this is fairly advanced latent class modeling for those of you who are already familiar with a more conventional latent class modeling. You're ready for the next step. So look at this now. When we have two latent class variables, you can have a model CA and a model CB. So you may want to circle this, model CA, model CB. And we're going to try to represent this idea of measurement invariance across the two twins by saying that for each class, you have these thresholds for the 11 variables. And they vary across the classes. So here's for class 1 down to class 5. These are different, corresponding to different conditional item probabilities. They're different also, as we see by the numbering. They're different, these parameters, over the classes. But they are not different across the two latent class variables. So the first latent class for twin B has the same numbering as the first latent class for twin A. So you have equality here, the same numbers here and here, down to the same numbers here and here. So that's the thresholds being held equal across the twins, still allowing them to be different across the classes, because that's the content of latent class analysis, to say that we have measurement invariance across the twins. And it doesn't need to be so. You may relax part of these equalities. By the way, here at the bottom of slide 135, you see how you plot item profiles for two different sets of variables, for twin A and then bar, plotting it for twin B following that. I will not go through the twin data output, but instead go to slide 139. So the question is, what's the difference between intercepts and thresholds? And the short answer that we can discuss more is that they're one and the same, but with opposite signs. Now, here are two twin models. So behavioral genetics modeling is quite easily done in Mplus. And we have been inspired by developments in the MX program by Michael Neal in Virginia, and tried to incorporate the technical approaches there, or the options there in Mplus in what we feel is a more simple interface. For those of you not familiar with the twin model, you have twin 1 and twin 2 here. Here's for one dependent variable, continuous, and you have three factors. This is the additive genetic factor, the common environmental factor, and the unique environmental factor. And what you want to study is the contributions, the strength of influence of those on the response, particularly how strong the genetic component is relative to the others. It gives you a covariance matrix for the two variables, y1 and y2. So this is the covariance matrix that looks like this. And from that, those two matrices, one for the dizygotic twins and one for the monozygotic twins, you can identify all of the parameters in a joint two-group analysis. And for Mplus inputs of that, you see the user's guide examples here. Now, for those of you who've done behavioral genetics analysis, that's standard fare, very simple to do. Now, we're going to jazz it up and look at the right screen and go back to the twins, where we have multiple indicators with a measurement invariance, and each twin having their own latent class variable. And we're going to introduce the three ACE factors behind here. That is, you can do this variance decomposition also for twin models, where in this case, the dependent variables for the decomposition are the latent class variables. For instance, if you have binary variables, this is where the liability model comes into play in behavioral genetics if the C's were observed. But you can actually have latent C's here, and latent class variables that correlate due to three factors, ACE. I've seen this kind of approach done in behavioral genetics applications except they do it in an ad hoc fashion. Conventional approach is 3 steps. You do a latent class analysis, then you classify people into most likely class, and then you look at the twin concordance, the agreement, or you do this ACE decomposition. But what I'm talking about here is a new approach where you can do it in one single step. And usually when you can do analysis in one step, you're doing better. Latent class variables are regressed on a continuous latent variable. So this is one example of where we bring together both continuous and categorical latent variables. So that one is ready for application. If you want to read about basic things about twin modeling, you can read Prescott's article in Behavior Genetics, where she looked at twin modeling for categorical observed variables. And then we have another article in Twin Research in Human Genetics on using categorical latent variables as well. So you may want to take a look at that. Now, we talked about conditional independence assumptions, and Linda talked about misfit in terms of bivariate statistics, residuals that were significant in the bivariate setting, using Tech 10. And Linda said if you have a lot of misfitting residuals, you may want to increase the number of classes, but sometimes you may just want to correlate 2 items that seem to be the only pair that contributes to misfit. So you can have a model like this, where you have the latent class part of the model here on the left, and then you add a way for these 2 variables, U2 and U3, to correlate. And one way to do that is to introduce a continuous latent variable that make them correlate over and above what is explained by the latent class variable. And this was an example in biometrics. They introduced that for the first time. You have the reference up here, Q10 Kuttner, having to do with a medical example. And this, the next few pages, which I will not go through, tells you how to go about orchestrating this residual correlation here. Because we want to spend our time with you on the most important applications, and therefore I will go forward quite far into slide 153. And actually, I think we should stop here and take questions. Because slide 153 then opens up a whole new set of modeling possibilities. So now we have a new approach here. We are trying, now when you're warmed up and you're no longer shy, we're actually going to provide you with a microphone when you ask a question. And we will record the frequency of questions asked before and after that innovation. But the first question was, what's the difference between thresholds and intercepts? And this is not something that we had taken time to explain very clearly. Mostly because it is explained in the earlier topics. But let me give you a short version. When you have a polytomous dependent variable, you can, if it's an ordinal variable, you can think you really have then, if you have 5 categories of an ordinal dependent variable, 5 categories, you will have 4 intercepts. Those intercepts, however, have to be ordered, one bigger than the other. And one way of deriving such a model that you will see in the Agresti book, Categorical Data Analysis book, is to think of that ordered variable as arising by categorizing an underlying continuous variable. So think about a normally distributed continuous variable. Well, actually, you don't have to think about it. You can actually draw it. I knew I could use this. Get to use this. So you have an ordinal variable like this, or response variable. Let's call it u star. Boy, I can see why I don't do this. And then you have these different thresholds, 1, 2, 3, 4 thresholds, which gives you categories 1, 2, 3, 4, 5, right? So this is u equals 2. So if u star falls in this interval, that gives rise to u equals 2 as an observed response. And this is one way of deriving the ordinal or ordered polynomous logistic regression model. It has 1, 2, 3, 4 thresholds or intercepts, and I'll get to the distinction in a second, but it has only one slope. And the slope is really the slope of u star equals alpha plus beta x. Well, handwriting is a little bit... I may have to use the eraser, but that would take too long. So the ordered logistic regression model has several intercepts, but only one slope. The reason why we work not with intercepts but thresholds is that thresholds correspond to these points on the assumed underlying continuous variable. So you think of this as if you're above this threshold but below this threshold. Does this show up? I better do it this way. If you're above this threshold but below this threshold, you answer u equals 2. So you think of this as thresholds. And however, they translate, say that you have a binary variable, then you have only one threshold, being below the threshold or above. That threshold is the negative of an intercept in the logistic regression. So if you have a logistic regression and talk about intercepts, an intercept, we will present it as a negative threshold. And we call these, in the formula world, we call these taus, thresholds. So it's a trivial difference of sign only. But the reason we talk about thresholds is because it comes from the ordered regression thinking. So with that, let's see who wants to grab the microphone.
So I just want to ask about the twin analysis again.
Which slide is that on, please?
Relating to 132.
Whoops. Sorry.
Did you say 141?
132.
132. And the other page?
That's okay. Must this analysis be done on mutually exclusive groups, although they're not because they're twins? Or can it also be used like in a repeated measures design where you're looking at the same person on 2 occasions?
Yeah. Okay. Question is recorded and understood, I think. So the question is, does that have to be twin A or twin B, or could it be a person at 2 time points? And the answer is yes. Everything is equivalent in the modeling thinking. You have repeated measurement, time 1, time 2. And of course, since it's measures on the same individuals, they have to be correlated. And here you model the correlation between the 2 outcomes, or sets of outcomes at the time points through the latent class variables, which will be the topic of tomorrow.
So I'd like to ask a question concerning page 122, and it's about measurement invariance.
120, let's get there
yeah.
first.
Let me do
and
that.
How can you check measurement invariance? Because I have a lot of question data, and I'd like to know if there are really differences and not only, I would say, measurement artifacts. So how can you control for that?
Okay, so the question is about measurement invariance or non-invariance, which we just alluded to briefly here because, again, it's a topic that comes up in the early days. Topic 1, in particular, we deal with measurement non-invariance testing quite a lot, and topic 2 as well. But let's talk about it a little bit. Do you want to start, or should I?
I don't even question as well.
So you have then this situation where you have, if you have a direct effect from x to u3, you do not have measurement invariance for u3 with respect to x. And the way you think about this is that the probability of answering yes here is not only a function of the latent class membership, but also a function of the gender that you have. So a yes answer the probability of a yes answer is influenced by the gender, and therefore not only by the latent variable, and therefore it's a non-invariance matter. So how do you test for it? Well, you could say, well, why don't I just include all of the direct effects for all of the 3 items from x? And the answer why you don't do that is because that is not an identified model. You cannot have all of those 3 direct effects and the effect of x on c. It will not be identified. And Mplus will, when the model is not identified, which is a big topic in itself, Mplus will protest and try to tell you that's not identified. Essentially, it will have a big problem computing standard errors of the estimates, and it will tell you so in no uncertain terms. Now, since you cannot identify, what do you do to detect this non-invariance? Well, one way of doing it is go through each of the u variables, regress each. In this case, you would do 3 analyses, where you have the model regressing u1 onto x directly. And if you have several x variables, you would regress u1 onto all of the x variables directly. And then you go to the next analysis, do the same for u2, and then the next analysis, do the same for u3. And you can see which ones of those direct effects are significant.
Page 126.
126.
Yes. Could you, for example, say that the effect of age in class 3 is stronger than in class 1? And could you test the significance of this difference?
Okay, there are 2 ways. You can either do difference testing. In this case, I guess we don't have chi-square, so log likelihood difference testing, where you run the model like we ran it, and in another situation where you run it holding those parameters equal, and then look at minus 2 times the log likelihood difference to see if that equality worsens the fit of the model. Or you could use what we call model test in Mplus, which does a walled test. And in that situation, you have to label those 2 parameters in the model command. And then in model test, you say, let's say you labeled them P1 and P2. Then in model test, you say P1 equals P2 or 0 equals P1 minus P2. So that's how you could do that.
So in both cases, you do chi-square testing, but in the first case, it's likelihood ratio chi-square testing. In the second case, it's the walled chi-square test approach. But that's very easy to do by these approaches that Linda mentioned.
Okay, do we have... Here we have somebody in the front.
Yep, microphone coming.
We're running Claudia around.
At frame 76,
76.
about bootstrap, there you recommend using at the highest 100 sample, 100 draws, and that seems to me, from what I've heard, pretty low. I often seen a number of draws about 500 or 1,000. Is this because of a different in the situation where you're using this method, or what?
Yeah, so I think the question is about the Tech 14 or the bootstrap likelihood ratio test. And we talk about 100 samples here. In this case, Timur Asparoho has written about this. He has come up with a sequential decision technique for limiting the number of samples that you have to draw. Essentially, you draw an initial set of samples to see if you can determine what the p-value most likely will be. And if it's indeterminate, you take some more. And if you take that approach, it turns out that very often you don't have to draw as many as 100. So you can get away with fewer than in regular bootstrapping. You all were not shy at all, I guess.
Okay. I've got a question on slide 97.
27?
9-7.
So I didn't get it before. Could you please repeat on
Is that right?
what the asterisk 0, asterisk 1, and asterisk 2 are meaning?
So an asterisk means that the parameter is free, and the number following the asterisk is a starting value. So Mplus has automatic starting values, so you don't need to give anything here. But if you want to give starting values, because, for example, you want a particular class to be the last class, then you can use asterisk starting values to do that.
Let me say just a little bit more about that to get back to the question about thresholds. And soon you will think that all of this is very easy and transparent. So, for instance, what does it mean that we have star 3 here? This is thresholds. It's not intercepts. Threshold thinking should be as follows. A threshold that is high, it's difficult to exceed. Therefore, the probability is low. So a high threshold, this is high, much higher than the others. High threshold corresponds to low probability. A low probability for these antisocial behaviors implies that we're talking about the normative class that doesn't misbehave, right? So that's how you put the normative class last, the big class that has low probability of engaging in any of these behaviors, low probability, high threshold. And 0 up there means that that class 1 has the highest likelihood of engaging in these items and is therefore the high class or the combined class. So that's how you think about it. In the beginning, starting values were needed for convergence. Now, we never use them. They're done automatically except when you want to reorder the classes. One reason for reordering the classes used to be that when you regress on X, the default reference class is the last, as we explained, with coefficient 0. But if the last class is not the one you want to compare to, we offer then results that are given for each and every one of the possible reference classes. So you have it all there in the output. So you don't have to give starting values to ensure that a class comes last for the reason that you didn't want that class last as a reference class when you regress on covariates. Microphone need over there, yes.
If you compare different models with different classes, is it necessary that the last model, that the last class is the largest class for k-1 to compare with k?
Please?
If you compare different solutions to decide how many classes you need, is it necessary that the last class is the largest class in one model?
No, not at all, no. In terms of deciding on the number of factors, no.
Okay.
The last class does not have to be the largest at all, no. In fact, if you use starting values and did 2 runs, one where the biggest class was last and one where the biggest class was first, they would get exactly the same log likelihood values.
Also on this sheet, if I want to compare class 0 against class 1, how to figure that out?
Comparing class 0 and class 1?
Yeah.
You mean
There is no class 0. They start at 1.
Okay, then, sorry. Class 1 against class 2.
Right.
And
Okay.
you want to compare them with respect to measurement parameters or
Yeah, now
structure?
I'm comparing to class 4. But if I want to see the logits of the class 1 against class 2.
You want to see that, let's see. You want to compare the,
So do you mean have a different reference class than class 4? Okay. So if you basically in a I don't know if I can speak. In a multinomial logistic regression, we give every class as the last class, right? So is that what you're asking? To have a different reference class in the multinomial logistic regression? We usually give in the output results for every class being last. But if you wanted to actually do that, then you would have to decide on the class that you want to be last. First run the analysis like this. And then let's say you want class 3 to be last. Well, you take all the numbers that you get for the thresholds for class 3, and then in a new analysis, you give starting values using the class 3 ending values. You use as starting values for class 4 in a subsequent analysis.
In the general case, that's done automatically by default.
I have a question about 110, slide 110.
110?
110. There are probabilities within classes. Is it possible to compare probabilities within classes across classes? Like, for instance, using marijuana, it's, 0.90 for the high class and 0.96 for the drug class. So can we say that people in the drug class uses more marijuana than the people in the combined class?
Like 0.90, compare 0.90,
Yeah,
0.96,
can we
for instance?
Yeah, for instance.
Yes, there's a very convenient feature in Mplus for doing that. The model constraint section, or possibility model constraint, you actually can express a probability like this in terms of the parameters. The probability is expressed by the logistic function 1 divided by 1 plus e minus the logit. The logit is the parameter, but you can write then the probability as a function of that logit parameter. So that probability will now be a new parameter that gets the estimate of which gets written out, 0.90, and its standard error. And you can actually then also do so you can either constrain them to be equal in the analysis and compare that to the analysis where they're not constrained equal. So that gives a chi-square test of the likelihood ratio kind. Or Linda's other alternative, use model test, where those two probabilities are given labels, like P1 and P2. And you have that walled chi-square test through model test to test that they are actually, that they're equal.
We constrain the logit parameters or the probabilities themselves. I couldn't understand.
The probabilities themselves.
As a parameter.
Yes, so you can actually work with the probabilities themselves. So you write P1 is equal to 1 divided by 1 plus e to the minus P1L, the corresponding logit. So you have that full flexibility working with probabilities if you want instead, yeah. It's the standard errors for the probabilities and the test and build on the so-called delta method for computing standard errors, functions of random variables. Yes?
I would like to know if it changed something to choose to decide your number of classes with or without covariates in your models. Like you say in the twin models that you have modeling in 3 times and you can do in 1 step. Does it the same thing for every?
Oh, okay. I think I know what you mean, but I have to confirm. Are you thinking about a situation like this, where you have a covariate in the model?
Yeah, you present everything on deciding the number of classes without covariates. Then you present how covariates predicted your C's, your classes. But are there differences if you decide your number of classes in the same time that you have covariates in your models?
I see, yeah. So the question has to do with deciding on the number of classes. Should that be done with the covariates in the model or without the covariates in the model? And that's a difficult question, which has been gathers quite a lot of attention now in terms of simulation studies and the like. For instance, Karen Nyland, who we talked about before, is working on a paper together with Catherine Mason, who's also done mixture modeling. And they're trying to simulate data to answer the question, which is the best way to go? But it's a good question. If you don't have this direct effect in the model, deciding on the number of classes shouldn't matter whether or not you have X in the model. You should get the same result. But if you have a direct effect here, you would probably get different conclusions on the number of classes if you did not use X versus if you did use X and you let X only influence C. So if you have this direct effect, first of all, if you didn't use X in the model to decide the number of classes, then this relationship would be misspecified. U3 is a function of C only, you're saying, but it's really a function of C and X. And therefore, you would misattribute how many people are in C, and therefore the testing would be affected, would be biased. So if there is a direct effect, working without X would potentially give you the wrong number of classes. Now, if you have the direct effect and include X, but only let X influence C, you would also potentially make the wrong decision. You would have to know that they should have a direct effect in there. So in conclusion, if you have no direct effects, it should not matter statistically if you have the X's in or not. But if you have direct effects, if you have measurement non-invariance, it can matter. So as a general strategy, we typically do not use the X's to decide on the number of classes as a first step. So no X's. But then we are not surprised if in some cases when adding the X's, you would get, first of all, different class probabilities, which is then an indication that if you try to decide on the number of classes with X, you would get different results than without X. But if you find those differences when you add X, I would try to explore the presence of direct effects to see if there's some measurement non-invariance that would explain that. But if you're interested in that, send me an email and I'll pass it on to the individuals who are writing papers on this to refer you to Monte Carlo study. I think their conclusion is it's probably better to try to decide on the number of classes without X's. Are we ready for a coffee break? And if so, how long should it be?
So let's say we come back at 3:35.